Hello, John.
Hello, how are you?
All right, I'm not sure if anybody's going to show up. I normally have quite a few people in here by now. Uh, I am going through a bad storm, so I was going to warn y'all that we might get disconnected. If we do, we'll just call it a day, and I'll suggest you hit some of the videos that are on week 6 and 7 of our Canvas page. So I'll tell you that anyways. Just make sure, like I said, if we get disconnected, that'll be it. If no one else shows up, I'll probably just cancel class and send everybody out with or I'll just send an email out to everybody since they didn't come and just tell them, hey, check this out. So you'll know how to use Gauss's law and that sort of stuff. But I'm glad you showed up anyways. You have any questions for me?
Uh, no question specific in terms of material. The midterm I did want to ask, once I start the midterm, the ID, I guess you had mentioned something regarding ID
Mhm.
at the beginning or before you take the midterm. Is that like, are all those instructions on there before I
Yeah,
go in
it
there and
gives you
start it?
those instructions, but just to make it easier on you, I'll read them to you real quick right now as well,
Okay.
because
Yeah,
that
that'd be
way
great. Thank you.
you'll just, I've seen it for a second time, so that might be helpful.
Okay.
Let's see if I can pull it up real quick. Not it, that's not it. 17 to 21. There it is. So when you go to do the setup, there'll be a text area where it says additional instructions. And in that area, it's going to say, during this exam, you shouldn't access other resources, a phone, tablet, notes, books, etc., or communicate with other people. Please stay in your seat and focus on the computer screen until the exam is completed. If an interruption occurs, briefly explain what happened by speaking directly to your webcam. And finally, remember that you cannot exit the exam until all questions are completed and submitted it for grading. When you begin, present your photo ID close enough to the webcam to easily verify your face matches the photo on the ID. You may cover up identifying numbers, but your full name must also be visible. After that, use the webcam to video all of the areas that will be within your reach while taking the test. You are allowed blank paper, and you may have an equation sheet that only includes the equations that were numbered in your textbook. You are not allowed to have sentences or names of laws or equations. You may have names of variables within an equation. You may also have constants with their units. You must show the front and back of every page of paper that will be within your reach during the test. And of course, that includes the sheet with the equations mentioned above. Good luck.
Okay, got it. Thank you.
No problem. And then it tells you again in the environment check, it says, make sure the air around your computer is clear of papers, books, phones, etc. Start recording. Slowly tilt, pan your camera, webcam, so a brief video can be made of the area around your computer. If the webcam is built into the monitor, just do your best and show the surrounding area. Then lay your webcam computer down and slowly show the fronts and back of each page of your equation sheets and scratch paper. You must make sure that the sheets can easily be read, even if that requires more time to slowly show that every section of each page. Remember, your instructor only allows equations numbered by your textbook author or explicitly allowed by your instructor. You are also allowed constants, SI prefixes, conversion factors, derivative tables, integral tables. Click stop recording when finished. So that's them.
Got it. Thank
Make it
you.
a little less stressful. Somebody else came in too. Yes, let me let them in. Hello, Tanner and Elron. Welcome to class. Anybody have any questions? All right, so it seems like no one has any questions right now. I'm still concerned about how few of people we have. Let me look at something real quick.
Excuse me, Professor.
Yes, go for it.
How you doing? Sorry, I was like on the waiting screen for a few minutes, but can I ask what I missed?
Yeah, you missed. John gonna ask me a question about the instructions that I have on the test, and I just read those instructions to him. So you didn't really miss much, in other words.
Okay, cool, cool. Thank
I
you.
did yawn several times, so you totally missed that.
Oh, dang.
So yeah, I just reminding everybody. Remember, you're supposed to have a photo ID, and they want you to put it, up where the camera can see the photo and tell that that photo matches your face, and that photo ID has your name on it. You don't have to show me the number, like if it's a NCDMV or VADMV number. You don't have to show that. All I really need is your name and your face.
Cool.
And then you're supposed to use the camera to hover over, show me your workspace down by your feet. You should have, maybe 4, 5, 6 sheets of paper, and each of them laid out one high, so you can pan over them and show me them, and then you can hold that up and one by one pick up the sheet and turn it over so I can see both sides, then do the next sheet, then do the next sheet, so on and so forth. So, yeah, that's all it's required. It's due not tomorrow, but Wednesday at 11:59 p.m.
Okay, gotcha. Oh, also, me and Bohan and some other people like finished our lab late, so like Bohan's still kind of on the way home, I think.
Oh, okay. Gotcha.
Yeah.
No problem. So yeah, the weather's not too good. I was just telling them, weather here is real bad. We had severe thunderstorm warning, so I was afraid our internet might go out. If it does, I've already put a whole host of videos in week 6 and week 7. All of them, every problem solved in them are really good for these chapters on 21 and 22, which includes Gauss's law and stuff like that. So definitely recommend you watching them and using them as further examples, whether you stick around for class or not. You should probably still watch those. You'll get a lot of learning takes place when you're trying to see how Gauss's law is actually implemented in special cases and stuff like that. And I've done some really tough ones and put them on my YouTube channel for that reason. So it just linked right to them. All right. Elron's back.
Sorry, I'm enjoying it.
No problem. All right. So really all we have to do is last time we covered Gauss's law, and I was looking in the notes, and I did a sphere that was uniformly charged with a total volume, with a total charge Q, but it was a conductor. And then I did a sphere. Oh no, it was a non-conductor because it's uniformly charged throughout. So I did that. If it was a conductor, it would have, of course, had the all the charge resides on the outside. I think I did one of those too. Looking at this, I did do the Gauss's law for a infinitely long straight wire, very thin wire. So I did that one. And I think what I did is I just explained what would happen in the case of a sphere. That was a conductor. Yeah, I even wrote the answers for a conductor. You would have had the electric field inside to be 0, but the voltage inside would be whatever the voltage had at the outer edge. So that's what I've done. What we need to do now, though, is we really need to do one for either an infinite plane, or you can just look at it as a plane, but you're really, really close to it. So I thought I'd do that. Let's go ahead and share my screen. I don't know why all of a sudden I'm yawning. I haven't yawned at all the whole day, but now I am. So here we go. All right, so this is a technique that we use for a plane. Is not unlike what we do for a cylinder. With a cylinder, you use what books used to call a Gaussian pill bottle, but none of my students are old enough to know what a pill bottle is. I normally have one in my pocket, which is kind of funny, and I carry it specifically because of that. But anyways, it's basically just a cylindrical. In my case, I have an aluminum one with a little lid on it, and you just put your medications in there that you got to take throughout the day. But the main thing is it's just like the shape of a soup can. So I often just use the term soup can. So what we're going to do now is we're going to use Gauss's law to predict and calculate the electric field both above and below a uniformly charged flat plate. And this plate, like I said, we'll consider it infinite in size, and I'll explain the details of that in a second. So the question is, what is the, ooh, that's a really bad looking Z. I don't like it. What is the E field above and below an infinite disk that is uniformly charged with, whoa, a constant charge per square meter. Sigma. So that's our question. And of course, the thing's going to take one more opportunity to erase itself just before I do my work, because it always does. Good, I got that. Got rid of that, but I got rid of something else too. So what we're saying is this surface charge density, sigma, is a constant. What that means is if you take a square inch of the disk that's charged and measure the charge on it, you'll get a number. If you take any other square inch of it, you're going to get the same number. And in fact, if you convert that coulombs per square inch to coulombs per square meter, then you'll get the same number for all of them as well. Okay, so here's my drawing. I'm going to imagine an infinite plane. And the infinite plane is going to look like this. Okay, and in reality, of course, it's going to go to infinity that way, and that way, and that way, and that way, and that way, all like that. So what I'm going to do is draw a coordinate system that has my z-axis right there, that has my y-axis right there, and has my x-axis right there. And my solution will be played out as follows. So first off, I am going to use the symmetry of the actual charge distribution to help me understand what the electric field is going to be like. In other words, what's it going to depend on, what variables matter, and what directions the electric field will point. So if you really think this is infinitely large and you start thinking about, well, wait a second, there's a charge right here. And if I'm looking for the electric field right here, then if I connect that point with the line, I'm going to get an electric field that way, which is supposed to be parallel to that little line I drew, but I drew a really unfortunate line choice and point choice because it made it so small I couldn't do anything. So I will regroup and do another one. Let's imagine instead right here, whoa, no, right here on the y-axis, there's a data point, a point in space, say, and that little point has a very specific charge there. And in fact, as a result of that charge there, the electric field at this location right here, which might be at a height z, for instance, that electric field is going to point that way. But since this is infinite, I know there is in fact another charge right here that is the same distance away to the left and right and the same distance away up and down. So it will in fact create an electric field along this line that points that way. Now, because of the symmetry, it's going to have the exact same magnitude as the first one I drew, and it's going to have the exact same y component except opposite in sign. So the y component, for instance, for the first one would have a negative y component, and the second one's going to have a positive y component, but they're equal in magnitude but opposite direction. The z component, on the other hand, would be exactly the same, so they're just going to add up. I could do the same thing with regards to a data point on the x-axis and then back here like this. In this case, the electric field would be that way, and the electric field would be that way. Again, by symmetry, the electric fields would all be the same strength due to the one blue point versus the other. And in fact, the y components would be 0 for the blue points, but the x components would be opposite of each other. So for instance, the front blue point is going to have an x component that points backwards, and the rear blue point is going to have an x component that points forward, but it'll be at exactly the same magnitude. So the y components in the red ones canceled out, and just like that in the blue one, the x components canceled out. So we can already argue that the vector field, the electric field, should have no y components and it should have no x components. It should only have, in fact, z components. Well, if it only has z components, that tells me a couple things. That tells me it's only going to point, in the case of sigma being positive, it'll point up above the plane. And if you go below the plane, again, sigma being positive, it'll point down. So for z less than 0, it's going to point down. For z greater than 0, it's going to point up. And I suspect if it depends on anything, it would only be how far away it is from the plane, which is a distance z, as I've drawn in this diagram. Okay, so that means my hypothesis is that E is equal to E of z k hat for z greater than 0, and E of z negative E of z k hat for z less than 0. So that's my hypothesis. Okay. That also tells me something. Since it only depends on z, it wouldn't make any sense for it to depend on x and y. Then if I keep a fixed z, then I should have a constant electric field. So that tells me I should create a Gaussian surface that is parallel to the plane, because parallel to the plane has a z equal a constant. So what I'm going to choose for my Gaussian surface is this green soup can, if you will. So here's my green soup can or my green Gaussian pillbox, it's going to go down to the surface of the plate of charge, and it's going to pierce the surface of the plate of charge, like so. And it'll be just like that. Okay. So with this in mind, I can say dA for the top of the soup can is going to be some dA in the k hat direction. Remember, the convention is that if you have a closed surface, which we do, then you always make your dA vectors point out from the surface. So that's what dA top is. dA bottom, again, we don't have to think in cylindrical coordinates or any specific coordinates what dA is, because we're not actually going to do the integral. We're just going to get the answer for integral of dA, which is just going to be A. And we can literally call it A. We don't have to call it power squared or whatever. So in this case, it's going to be negative dA k hat, because again, by convention, it has to point out from this volume. And then finally, we're going to have a dA soup label, which I'll indicate with SL. Okay. The dA for the soup label is, in fact, you can call it dA. And if you recall the little intro I did for cylindrical coordinates, there is, in fact, a R hat for cylindrical coordinates. And that's what we're going to say. The reason I'm using it is, one, it's already invented, so I don't have to make up a name and I don't have to describe it to you. And obviously, I'm still going to describe it to you because I'm the teacher, and that's sort of one of the things we do. But in fact, that R hat would have a X component that is cosine theta and a Y component that is sine theta. And in fact, it would be R hat is equal to cosine theta I hat plus sine theta J hat. Notice it has no K components. It's only a vector in the XY plane, and it points radially outward. Okay. So, and theta would be, of course, the angle measured. If I'm looking down the Z axis from above, it'll be measured counterclockwise from the positive X axis. So now I can do my left-hand side of Gauss's law. Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. I'm going to say the left-hand side. And the left-hand side is going to be the integral of E dot dA. And remember, the little circle on the integral doesn't mean there's any different math. It just means you got to remember that this is not valid unless you're doing it over a closed surface. So you got to take into account every part of it. So this is going to be an integral over the top plus an integral over the soup label plus an integral over the bottom. Okay, so that's really what it's going to be. I can say integral of E of Z k hat dotted with dA k hat plus integral E of Z k hat, and I'll put a plus or minus here because I'm doing the soup label. So I've actually got to go through the area both above the plate where E of Z k hat is positive, and then below the plate where the E of Z k hat should be negative. So I've included both of those, and it looks like we might run into problems. But when I put in the dA R hat, I can immediately see that that problem is taking care of itself, because K hat dot R hat, K hat is only in the Z direction and R hat only in the X and Y direction. So that part's clearly going to be 0. And then plus integral negative E of Z K hat dotted. Actually, let me regroup on this one. I'm going to write this third integral down here. I'm going to say plus, whoa, Nelly. It's so helpful when it does that. I'm going to say plus integral of negative E of Z k hat, because now we're integrating the bottom, and remember the electric field points down at the bottom. And of course the dA also points down, so I have to write negative dA k hat there. So the upside of it is that negative times a negative gives you a positive. So basically, when we do the integral over the top, that means z equals a constant. Therefore, we just get e of z times the integral dA top plus this guy, the r hat dot k hat, or the k hat dot r hat. This one's just going to go to 0, so we ain't got to worry about that at all. So I'll say plus 0. And then I'll say the other one also has integration over the bottom, which means z equals a constant. And because z is a constant, that means the e of z is also a constant, and it can come right out in front. And I'm going to say e of z integral dA bottom. So what you ultimately get is just 2e of z times a, where a is literally the area of the top or the bottom, which I'll write like this. Okay, so that's the left-hand side. Now we can do the right-hand side. The right-hand side, we have Q enclosed over epsilon naught. So that's 1 over epsilon naught times the charge enclosed inside of that Gaussian surface, which you might look and say, oh, it's this little bit right here. So can anybody tell me how much charge is enclosed in there? You might need to read the original problem. All right. Well, in the original problem, it said that actually, let me check something real quick. I do see a chat came up. No, that was not the comment I was hoping for. So, okay, in the original problem, I said that the infinite disk is charged with a constant charge per square meter sigma. Charge per square meter sigma. Can you now use that, you think, to tell me possibly how much charge is enclosed inside that little cylindrical soup can or whatever? Think about the units of sigma. We want charge, and we got sigma having units of charge per square meter. What do you think you're going to need to multiply sigma by to get the charge? Okay. So the square meter is a unit of what? Length, density, volume, area, derivative with respect to time. What is square meter a unit of? Yes, it's meters squared. Thank you. So remember the charge or the original assignments I gave you was that dq would either be equal to lambda times dl, or it'd be equal to sigma times dA, or it'd be equal to rho times dV. That's the three scenarios. In this case, we're dealing with sigma. So the fact that it's sigma means it's charged per square meter. So if we knew how much area was enclosed, how much area of that plate of charge was enclosed inside the soup can, then we could just multiply that area times the sigma. Does anybody have any idea what that area is? And by the way, it doesn't matter if you know it or not, because if you have it on opposite sides of an equation and it's on both sides, then it's going to cancel out anyways. All right. That's okay. It looks like you aren't quite getting it. That's not a big deal. What we notice here is that soup label, or excuse me, that soup can, the green soup can that we're looking at in this drawing here. Okay, that green side comes down and hits the disc, and when it hits the disc of charge, that is, it traces out this area right here. And that area, of course, is the same as the area up top. So its area is actually A as well, just like the area from the other one. So because of that, we can say that the total charge will be sigma times A. Okay. Now I can say left-hand side equals right-hand side. And when I do that, I have 2E of ZA is equal to sigma A over epsilon naught. And we can see that the A's cancel one another out. And in fact, we can go ahead and report that the electric field E is equal to sigma over 2 epsilon naught k hat for Z greater than 0, and negative sigma over 2 epsilon naught k hat for Z less than 0. And in fact, the discontinuity is a very specific amount. It's one that I've talked about before. It turns out to be discontinuity that notices sigma over 2 epsilon up, and then a sigma over 2 epsilon down. So you add those two and you get a sigma over epsilon naught. So the discontinuity which you might call, let's see, E plus side minus E minus side at Z equals 0 is equal to sigma over epsilon naught. In other words, let's graph it real quick just to look at this. So if you graph E on the vertical axis and you graph Z on the horizontal axis, what we know is that the electric field right here is sigma over 2 epsilon naught, and goes like that, and has an open hole in it on the end. And what we know is that, I should probably get rid of a little bit of that, make some more axis here to make it look right. Okay. And what we also know is right here, we have an open hole again. And the electric field here is negative sigma over 2 epsilon naught. So if you take the electric field at the positive side, which is sigma over 2 epsilon naught, minus the electric field on the negative side, which is minus a negative sigma over 2 epsilon naught, you do get, in fact, a sigma over epsilon naught, which is what your book talked about and what I've mentioned a couple times myself. So that's the common answer, is basically electric fields, the components of electric field perpendicular to a surface is continuous unless there's a surface charge, and when there is a surface charge, it's discontinuous by an amount surface charge divided by epsilon 0. Any questions on that? Now the big thing is we should be able to now predict what happens when you have a positively charged plate and a negatively charged plate. So consider two plates. So what I'm going to do is I'm going to imagine a charged plate here that has a charge of positive, and you can say basically it's going to have a charge of plus sigma. And then right next to it, we have, and I really want to draw it even closer together so we can show that they're so close that we can treat them like they're infinite, but then I won't be able to draw stuff inside of it that you can see. So I'm going to just leave it spaced out, and we're going to pretend like it's really, really a small distance compared to the distance to the side. Okay, so if we take two plates like this and put them side by side, we've got one due to the electric field due to the positive plate, and we've got an electric field due to the negative plate. The positive plate on this point right here, everybody see the blue dot I just drew? At that point, notice you're to the right of the positive plate. Which direction will the electric field due to the positive plate point? Will it point to the right, to the left, up, down, or into the page, or out of the page? That's right, Elron. It will point to the right. Okay. And that is what we'll call E positive. Now imagine in that same location, which direction will the electric field due to the negative plate point? So again, the answers are to the right, to the left, up, down, into the page, or out of the page. And we're looking for the electric field due to the negative plate. Now the negative plate is exactly parallel to the positive plate, and in fact runs really deeply. Since it's infinite, it runs all the way to the end of the universe up, and all the way to the end of the universe down, and all the way to the same thing for the negative plate, all the way to the end of the universe up, all the way to the end of the universe down, and all the way to the end of the universe back behind the page, and all the way to the end of the universe out towards me. Okay, that's how this plate is oriented. So in which direction does the electric field between those two plates point if I'm talking about the electric field due to the negative plate? It's not into. Remember, an electric field always points the direction in which a positive charge would tend to move. If I stuck a positive charge to the left of that negative plate, what would it do? Yes. So I'm asking you, forget about the positive plate. Just think about the negative plate. With just the negative plate there, right there where I drew that little blue dot under the E plus, in which direction does the electric field point at that particular location due to just the negative plate? To the right, to the left, up, down, into the page, or out of the page? Yes, still to the right. So that's the key that you see is when they're oppositely charged plates, the two are supporting one another and creating an electric field that's twice as big as it otherwise would be. So instead of sigma over 2 epsilon naught, it's going to be sigma over 2 epsilon naught for the positive one, plus sigma over 2 epsilon naught for the negative one, and that gives you a sigma over epsilon naught. So in fact, the answer between these two is sigma over epsilon naught. That's the total field. Between the plates, that's the total field. Now, to the left of the positive plate, which direction does the electric field point due to just the positive plate? So let's say at this dot right here. Yes, it points to the left. Again, it points in the direction the positive charge would go, and that is E due to the positive plate. At this point right here, which direction does the electric field due to the negative plate point? So positive charge, ignoring the positive plate, just thinking about the negative plate, a positive charge is going to want to go to the right. So that's how we know that the electric field points to the right here due to the negative plate. Okay. So on this side, we get E equals 0. Now I got to do the same thing on the other side. At this point right here, in which direction does the electric field from just the positive plate point? Yes, this one's to the right. So we'll say that's E positive. How about right here, due to the negative plate, which way does the electric field point? This is just due to the negative plate. Okay, so yeah, some people are overthinking it, and I'm thinking that these are supposed to be fairly easy. So let me regroup here for a second. So what we did is we first used Gauss's law to find out how the electric field behaved near a charged plate. And we're really saying near a really close to a charged plate. And what we found is that it'd be a uniform electric field. In other words, it doesn't depend on distance or anything. It's just a constant, and it points away from the plate if the plate is positively charged, and towards the plate if the plate is negatively charged. So what I'm doing is considering what happens to the electric field in between the two plates, on the left side of the two plates and on the right side of the two plates. And the easiest way to do that is to first figure out what the positive plate's going to cause, and then figure out what the negative plate's going to cause. And since they have the same magnitude, then if they add together, they double. If they subtract from one another, then they cancel each other out. So that's why I'm going through this plus and minus. So what I've already asked you, and you got the right answer for, was in which direction does the electric field due only to the positive plate point on the right hand side? And you guys said to the right. Now I'm asking you, only with regards to the negative plate, in which direction does the electric field point if we're talking about that little blue dot on the right hand side? So which direction is the electric field due only to the negative plate, and which direction is the electric field on the right hand side pointing? Yes, to the left. And that's the whole reason we did this exercise, is so we'd see that in fact for a parallel plate capacitor with oppositely charged plates, which is what a capacitor is, you get electric field being 0 outside of the capacitor, but the electric field actually doubles inside. In other words, it's twice as strong as if it were one plate. Okay. And not only that, that gave us the actual answer. The answer is sigma over epsilon naught, not sigma over 2 epsilon naught, but sigma over epsilon naught. So that was something you haven't learned about yet, but it's called a parallel plate capacitor. Which I'm sure you all recall from Back to the Future with the flux capacitor. Okay. They actually use the word flux, which we've been using, of course, and they use the word capacitor. And it is an actual circuit element that's really, really helpful. There's basically two circuit elements that are extremely helpful. One's a capacitor, the other one's a solenoid. And then, of course, you always have resistances, but the capacitor and the solenoid are the inductor, is a more normal name for it, not solenoid. Sorry about that. A solenoid is a special type of inductor, but an inductance and a capacitance act on currents in sort of the opposite or the complementary way. So one actually causes an AC circuit, makes the voltage lead the current, and the other makes the current lead the voltage. So they act in opposites, and you can actually exploit that to use resonance, and then that allows you to do really high-powered stuff. And we'll get more to that as the semester goes on. But anyways, we now have what's needed for making a capacitor, or for calculating what the capacitance of a capacitor is. We just needed to know that the electric field inside is, of course, constant. What I will also say here is by symmetry, blue and red arrows. Actually, I could have done that a little better. By symmetry, the E field only has K/Z components. Okay, so I just wanted to, since I covered it really well, I took the time to explain it to you verbally with pictures, but I didn't actually write any words on the pictures. I wanted to reiterate that those little blue and red arrows that you see at the top of the diagram are us discussing the symmetry of the problem, to show that the blue and red arrows are going to have all their X components and Y components cancel each other out, and leaving only the Z component. So that's why I took the time to write that. It is very small, but when you open it, of course, you can zoom in on it just like I did there. Any questions on that stuff? Okay, so I'm certain I've done more than enough Gauss's law problem examples. In fact, you've got a ton more on my YouTube channel. I just did a search on my YouTube channel for the word Gauss, Gauss, and it pulled up, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 really accurate hits. The first 10 are very accurate. After that, some of them are like, I just happen to cover Gauss's law at the end or stuff like that. So, of course, the newer ones are often a little better, but some of them are just really, really good, period. So, anyways, you can find plenty of examples of Gauss's law on my page, and I try to explain each of them like I do here. Hopefully that's helpful. My goal here is wanting you to understand why you can do this so easily. And to do that, you sort of need to understand the mathematical machinery that's going on. So I try to do that by showing you that mathematical machinery. So hopefully that helps. Anybody have any questions on this or any of the other Gauss's law type things that we've covered? All right. And by the way, you might want to do this on your own. This is an entirely separate scenario that I just did where I took those two parallel plates and I made one positive and one negative. A typical question that comes up from time to time, like in conceptual questions, is what if you had two positive plates? And what if you had two negative plates? So you can work out these same 6 scenarios that I did here, but you could do it with two positive plates or two negative plates. That's worthwhile to think about. And it'll also help give you practice on answering the questions that I was asking before when you had a positive and a negative plate. All right. So this allows us now to move into the next chapter, which is chapter 23. Chapter 23 is basically on voltage. So if you think about, let's say, a mass sitting on the ground. So here's my ground, like that. There's a mass sitting on it. And I imagine coming up to it and saying, okay, let's apply just enough force to it where we're canceling out gravity. So obviously that would be a force equal to mg, but we're going to push it up on it with a force mg. Now that's enough to take away what the earth is supplying, what the ground is supplying by holding it up. And if we just were able to go so slow that we can wait until a random molecule hits it from the bottom side, then it'll move up just a little bit. And then we wait more and it'll move up a little bit more. And we just keep on doing that where we're constantly providing that force, but not letting it get lower. What will eventually happen is the ball will move up to a height. Let's say I'm going to put my axis right here. I'm going to put my x-axis here, and I'm going to put my y-axis here, and I'm going to say this is a height y. Okay. If I did that, then I can calculate the work done, and the work done would be work equals the integral of f dot dl. And of course, doing so, going so slow that we don't give it any kinetic energy, then that allows us to just look at what we've done in terms of putting force in. So I'm going to take the integral of mg, and in this case, the force is actually in the j hat direction. And the object is actually going to move from y equals 0 to y. I will use the range of integration to dictate which direction I'm going on this line integral. So I'm going to say from y equals 0 to y, and I'm going to say the positive coordinate direction is what my dl is. So in this case, it's dy j hat. I'll use the linearity of the dot product and the fact that mg is a constant. I'll put the mg out in front. That's because it's a constant. And I'm going to put the dy here, and then I'm going to put j hat dot j hat here. And that's because, again, the dot product is linear, so we can allow that dy to slip right through it. This actually allows me to calculate j dot j, which j dot j is 1, because the magnitude of any vector with a hat symbol on it is 1. And then 1 again, and then cosine of 0 degrees, which is all equal to, I got ready to say it, but I wrote it the wrong way, which is all equal to 1. Okay, and it's 0 because the two vectors are in fact the exact same vectors. So that's a whole different story. But now we have actually what the work done is, and the work done is the integral of dy from 0 to y multiplied by mg. So I ultimately get just mgy. Okay, that is our potential energy. Okay, so we define potential energy, the change in potential energy is equal to the work done. That's the general scenario. In this case, it was the work done by us. So if you put work into a system, you can increase its potential energy. And that's what we did. What we're saying is the potential energy at the ground was 0, and the potential energy at the top is mgy. And since we got the work done was positive mgy, clearly the change in potential energy is mgy minus 0. So that's just the way we compute things. Now, what we'd like to do is do something similar to that with electricity and magnetism. So we're going to imagine, for instance, a parallel plate capacitor. Let's say right here and here. Okay. Now, what I'm going to try to do is I'm going to try to do an exact parallel. So I want to increase my potential energy. So if I do this with a negative particle, which I like because a negative particle is a more realistic scenario, I can do this with a negative particle of charge Q, for instance. Okay. If I want to increase its potential energy, then I'm going to take it from this place where it happens to be quite comfortable, because these are all positive charges on this particular plate, because this is the positive plate, and these are all negative charges on this plate. So if I actually cause this to move to here, okay, and let's say this distance is d, okay, then the work done in this case is equal to the integral of f dot dl again. And I'm going to supply just the right amount of force to do this. So I'm going to do just like I did before. In other words, I don't want to do more than mg in the case of gravity. In this case, I don't want to do more than q times the electric field. And the electric field is a constant, so that helps me. So I'm going to say integral of, and we can go ahead and make a coordinate here if we want. I can go ahead and call this the y-axis, and I can call this the x-axis. And then we're going to say the force we're going to apply is Q times E. And that's going to point, of course, in the j hat direction. And then I'm going to go from y equals 0 to d. That's me using the coordinate, or excuse me, that's using the range of integration to specify which direction I'm going. So I'll just use the positive coordinate direction for the dl. So in this case, the dl is going to be dy j hat. So when I get this, the q and the e is, of course, a constant, but I can do again y equals 0 to d of q e dy j hat dot j hat. So that's me using the linearity of the dot product. And that tells us that our answer is 1 times cosine 0 degrees. So that's 1 again. And in fact, what I get is Q times E times D. That's the work done. Okay. That's the work done. And that also is the change in potential energy. And it has units of joules. Change in potential energy in joules. And just in case you weren't one of the people that had me last semester, I'll remind you that a joule is about as much energy as it takes to get a really nice, red, delicious apple. You know, when they're in season, they're kind of good, and the water almost squirts out of them when you bite them. So you take one of those good, red, delicious apples and you pick it up off the ground and lay it on a tabletop. That's about 1 joule of energy. Okay, so that's a nice way of thinking about it. What I've just done there is I calculated potential energy, and in fact, I found that the potential energy technically went down, because let's not forget that Q is actually a negative number. So when I multiply Q times E times D, I'm going to get a negative number. So the potential energy of this thing actually, oh no, it actually went up. Sorry about that. It's the potential energy actually went up because we actually got to a place where it was less comfortable being. It sort of did the same thing as the ball going up in the air. If I would have tried to take that into account, I probably should have put a negative in front of it, and that would fix the charge. I just didn't write that. I was trying to work with just the magnitude. But the main thing is we do have a potential energy that's measured in joules, but now we're going to introduce something called an electric potential, and that is something different. So if I wanted to figure out how much energy any random charge could get, then I wouldn't want to use the potential energy, because the potential energy made me use the charge Q. Okay. So since it made me use the charge Q, one thing I could do is just like I did when I was dealing with Coulomb's law. When we first studied Coulomb's law, we had Q1, Q2 over 4 pi epsilon naught times R squared. And that gave us a force in newtons. But we wanted to consider what could happen to the space around a single charge, and what kind of effect would that have on yet another charge. So what we decided to do was, let's divide out that second charge so that we get, instead of newtons, we get newtons per coulomb, which would be the amount of electric field strength. So that allowed us to not be worried so much about action at a distance and all that good stuff. Well, if we do the same thing here, we're not necessarily attacking work done over a distance or anything weird like that. But what we are doing is taking the impact of the particular charge that you're using out. So I can define a quantity like this. I can say delta V, which is VB minus VA, is equal to delta U over Q. Okay. In other words, by doing this, I can take the effect that it had on an electron. I can take that particular part out. So instead of Q times E times D, I just get E times D. And if I really wanted to know how much potential energy, as opposed to electric potential, if I really wanted to know how much potential energy a particular particle got, I just have to take that ED and multiply it by the charge of the particular particle I want to use. So this tells us that this new quantity V, which is called the electric potential, or the voltage, it actually has units of joules per coulomb, which we define as the volt, okay, which is signified by a capital V. So a joule per coulomb and a volt are the same thing. Now, if we took that back and looked, what we'd say is the change in potential energy, if you want to calculate what's going to happen to a charge in moving from one place to another, and we wish to use, say, the force acting as a result of the electric field, then the change in potential energy is going to be the negative of the work done by that force. Ooh, I wrote W instead of F. So negative F dot DL. This is force due to electric, field. So work is that. Well, if I wanted to then say, well, what is delta U over Q, which really is the delta V, then I have to take this integral of f dot dl, and I need to divide it by q, but we already know what f over q is. Can anybody recall what f over q is? Yes, it's the electric field E. So we now have E dot dl. So that's actually it. This is our big sort of defining moment. We're going to say delta V, which is VB minus VA, is equal to delta U over Q, which is in fact the negative integral from A to B of E dot dl. This is our big result for this chapter. This is what we need. So that tells us how we can get it for any particular electric field, so on and so forth. You can calculate things, the same things we did before. For instance, you can calculate forces, you can calculate accelerations. But what we've done here is we've made use of some neat mathematics that I don't think I explained to you guys before, but in principle, what it says that is that if you have a field, in this case, a vector field, and for us, it's the electric field, but we could also consider force being a field and do it with force if we wanted. But in this case, we're doing the electric field. So if we had a conservative vector field, and what does that mean? A conservative vector field is one defining quantity. So we could actually just write it as 1 E is a conservative vector field. And that means it voted for Reagan. No, not really. It means that you can make a conservation law based on it. Okay. And in fact, what we generally use, so sometimes we even put this, instead of being number 1 and number 2, we sometimes just call this number 1. E is conservative. And that's because del cross E is identically 0. Notice I put a triple equals bar on there. What I mean by that is when you actually compute this thing, and this thing, by the way, that I just wrote there, that del cross E, that's called the curl, C-U-R-L. It's also called the rotation, which they abbreviate with R-O-T, and stuff like that. But anyways, when you compute all that, you're going to be basically taking the determinant of a matrix. The first row of the matrix is the I hat, J hat, and K hat vectors. The second row is the partial with respect to X is the first entry. The partial with respect to Y is the second entry, and the partial with respect to Z is the third entry. Notice they're not acting on anything yet. They don't act on anything until you start doing the cross product, or excuse me, until you start doing the determinants. And then the third row is going to be E sub X, and then E sub Y for the second entry, and then E sub Z for the third entry. So when you compute that nasty determinant, whatever way you want, what comes out is, some hodgepodge of derivatives of E with respect to X, derivative of E sub X with respect to Y, derivative of E sub Y with respect to X, derivative of E sub Z with respect to Y, all these different terms. If that turns out to be identically 0, then you have a conservative field, and you also have a field that is curlless. It has no curl. And if you have to put a particular X, Y, or Z value in there, or a particular set of X, Y, and Z in there to get it to be 0, then it's not a conservative field. So that's what I mean by is identical to R. That's also why I put that triple equals. Well, that's kind of cool, because if any one of these things that I'm writing down is true, then they're all true. I thought I heard somebody. Did somebody have a question for me? Okay, so the next part of this is 3. Then it turns out that the integral from A to B of E dot dl is just equal to negative of V at B minus V of A and is independent of the path. Remember, this is a path or a line integral, as all works are, and E dot dl is definitely a work scenario. So when you take a line integral or a path integral, you actually have to specify the line that you're going along. Well, what this is saying is, hey, because this field's identical, or excuse me, because this field is conservative, it doesn't matter which path you take, they all will give you the exact same answer. And that answer is going to be related to something crazy, some scalar function V, evaluated at the final point minus some scalar function V evaluated at the initial point, and then take the negative of that. So that's kind of neat. It tells us something about this V, and in fact, it tells me I should have written the other one first, but never mind, I've got that in already. 4, this is really should have been 3, and the other one should have been 4, but I got excited about writing the integral. So I'm now going to use some cool mathematical symbols. We get to write an upside down backwards E. And in math world, that means there exists. So there exists a scalar field, which you may also call as a scalar function, V. And now here's some more fancy mathematical stuff. They do that, which sort of looks like a cursive lowercase s followed by a cursive lowercase t. And it actually means such that. That's where it came from. Such that E, the electric field, is equal to the negative gradient of V. Okay, so this tells us, hey, that V that was in line 3, you shouldn't have seen that already. That should be in line 4, and this should be line 3. But that V is kind of interesting, and in fact, you can take the gradient of it, and out pops the electric field. So it can get us back to that vector situation that we working with before, even though now we've learned a way to work with it in a scalar way. Okay. And then there's another one, and actually there's 2 more, but I'll put number 5 here. The closed integral of E dot dl is equal to 0, period. And that should make sense, because if you look at 3, what the closed integral says is we're actually going from some point in space, let's say A, which has a value of x1, y1, z1, and we're going to go do some stuff. All these crazy paths we want to choose is fine. But the main thing is, since that closed integral, since it's got that circle on it, that means we have to end right back at A, which is x1, y1, z1. Well, if that's the case, then line 3 says we're going to get VA minus VA, that's 0 times -1, and that's still 0. So that's what that says. There's also another thing that comes out of this, and basically there exists a exact differential equation that can be used to describe this electric field. That's going it's going way beyond my bedtime, because it's been such a long time since I've had a differential equations course. So I'm a little rusty on the terminology as well, and it's really way beyond what's expected of you. So I would just mention that there is another expression to it, but the cool thing is what we've happened upon is a scalar function V, which we call the electric potential, that allows us to do problems with scalars instead of with vectors. That means the problems are going to be a lot easier to deal with, because I don't have to find a x component, a y component, a z component, and then only add the x, y, and z components to other x, y, and z components respectively, and then get an answer. This one I can just calculate plus and minus signs, because they're all scalar numbers. So that's a really big deal, and that's a wonderful thing to find out in physics, and it gives us a whole different perspective on how to do physics. This is, in fact, why we were able to do conservation of energy problems in chapter 7 and 8, because it turned out the gravitational field is a conservative field. And because it's a conservative field, that means that that del cross F for gravity is 0, that means there's a potential energy, which if you stay close to the radius of the Earth from the center of the Earth, then that potential energy is just M times G times Y. But if you go distances away from the center of the Earth that are comparable to the radius of the Earth, where you're going like 2, 3, 4 times the radius of the Earth, then you actually have to find a different potential energy. That potential energy turns out to be negative G, mass of the Earth, mass of the object divided by R. And that's the ultimate potential there. But it's a scalar potential, so you can work all the problems with it again. And basically what you're getting is energy sloshing back and forth between potential energy and kinetic energy and stuff like that. So basically that whole scenario that we did with conservation of energy, we can sort of now do that with electricity and magnetism by applying these equations. Anybody have any questions on that? All right, well, I am going to give you guys a 10-minute break. So let's take a break and come back at 6:53, and we'll finish up what I'm talking about here and solve some more problems, and then let you go. I will be here, by the way, so y'all can talk to me. So if you have questions, you can ask them now. If you're not doing anything, you can also look around at the stuff I've put up on our Canvas page for the various videos and whatnot. I'm going to stop. Luckily, so now it's recording again. So I did manage to do that. Thank y'all for having my back. What I wanted to do is first on the notes that I had, I went ahead and made this change. So let's go ahead and share my screen to show you this. Remember, I mentioned to you that I technically should have used a negative on that force when I was calculating the change in potential energy of moving the negative charge from one place to the other. So I went ahead and made some notes on that just to make sure you guys knew what was going on when you look at it later. So let me explain it to you now so it don't seem so foreign. It's coming. Okay. So I made those notes in green. It says, note, since Q is negative, the force should be negative Q times E times J hat, because notice a Q being negative means Q E J hat would literally point in the negative J hat direction. And if I put a force in the negative J hat direction, that's not going to cancel out the force of gravity. It's going to add to the force of gravity. So I technically have to put a negative in front of that. I also said since Q is negative, the force should be negative Q E J hat. So the correct signs are in green. So then all I did was I just carried the negative through, and you end up getting negative Q E D equals delta U. But remember, Q is negative too. So a negative times a negative gives you a positive. So ultimately that left-hand side is positive, and me moving the negative charge from the positive plate, which is where it was really, really comfortable because it was right up against the things that it's attracted to, up to the negative plate where it's really uncomfortable, was an increase in potential energy delta U. So that delta U, which is U final minus U initial, as essentially all deltas are final minus initial. Because of that, we get a increase in potential energy. So anyways, I just want to make sure I did that. Now, what we're going to do is we're going to look at a scenario with a charged particle again, and basically in a parallel plate situation. So let me draw the diagram that I'm talking about. So what I'm going to have here is a positively charged plate. I'm going sparse on my symbols here just to save some time. And what I'm going to imagine is a positive particle sitting right here. Actually, let's make a positive particle let's make it red. So there's a positive particle sitting right there. That's going to be position A. And then we're going to imagine moving that particle over to here, and that's going to be position B. Okay. Now, what I want you to understand is there's two different quantities we're dealing with here. There's potential energy and there's electric potential. So the potential energy for the positive particle when it's right here next to the positive plate is high. So we're going to say this point has a high potential energy. Okay, and that's the thing that's measured in joules. Okay, but we also have electric potential. Electric potential is basically the voltage. And in fact, we know that high voltage is the positive end of the battery and low voltage is the negative end of the battery. So this is high electric potential as well. And that quantity is measured in volts, which are joules per coulomb. Okay. Over here, we're going to have a low potential energy. And we're going to have a low electric potential. And that is like duh, because you learn from Ohm's law that basically we're picturing these little positive charges running from the positive side of the battery or the power supply, the red side, to the black side, which is the low voltage side. And that's exactly what positive particles do. If we look at it from a Coulomb's law perspective, we see that when it's at A, this positive particle is not comfortable because A is right next to the positive charges. The positive charges on the plate are repelling the positive charge that's free to move. So the positive charge is going to run away to the negative plates. And then when it gets there, it's going to be pretty happy and stick around. So everything in this drawing is doing exactly what we expect it to do. And that allows us to use our ideas about voltage and potential energy and that sort of thing. So in fact, what we're going to remind you with is I am going to remind you that delta V, which is the change in electric potential, which is the potential at B minus the potential at A, assuming A is the initial and B is the final. You could also do final and initial if you wanted. That's actually equal to delta U over Q, which of course is negative integral of E dot dl. Okay, so that's our big important result that we're going to use over and over and over again. And I keep telling my students in this class that there's going to be two major problems that are sort of big paradigms for the course. One of them is either use Coulomb's law or Gauss's law to find the electric field. Use this equation right here after you have the electric field. Use this equation to calculate the electric potential between one part of an object to another. So for instance, say from the positive plate to the negative plate, or from the negative plate to the positive plate. And then part 3, use C equals Q over V to calculate the capacitance. So that's like a 3-step problem that uses 4 or 5 different concepts. So it's a really big problem in 242. And it's sort of the, I don't know, it's sort of like a litmus test. If you can't do those 3 parts, you're not really supposed to be able to survive the class. Now, in addition to that, there's another one just like it for the magnetic field. And in fact, in that one, you either have to use the law of Biot-Savart or Ampere's law to calculate the magnetic field. Then once you have the magnetic field, you use an integral definition of the magnetic flux. So it's just like using the integral formula here for voltage, but in this case, we're using it for flux. And then you're going to use the definition of inductance or self-inductance to calculate the inductance due to that flux. And therefore you have the inductance of a solenoid or a parallel wires or a toroid, which is basically, if you imagine taking a donut and wrapping wire around it all the way around like this around the whole donut, that would be a toroid. So anyways, those are two big processes that you should be able to do upon completing this course. And we're now doing part of that. We've now done the Gauss's law and Coulomb's law, and now we're doing the voltage part. And after this, we can then do the capacitance part. So that's one scenario. Now, what I want to look at next is what about if I did this with a negative charge? So if I stuck a negative charge there, what would happen? Well, if you stick a negative charge there, let's say I'll do this one in, let's do it in green. So now I put a negative charge right here at A, or excuse me, at, I think I actually wanted to call that, did call that B, didn't I? Yeah. Okay, so in this case, I'm going to call it A, and then I'm going to call this B, because it's supposed to be A is the beginning and B is the end. So if I put a negative charge there, what I have is the same questions I had before. So is this a high potential energy or low potential energy? Is this a high electric potential or is this a low electric potential? Can anybody tell me whether that is a high potential energy at A? Remember, the potential energy in gravity, we know high potential energy means you're really high, far away from the attractive thing. So you could actually fall, and that potential energy could be converted to high speed, and then you hit the ground, and that would hurt. So right now, if this electron was, this negative charge was free to move, would it run away and go really fast, or would it stay right where it is? If it stays right where it is, then it must be at a low potential energy. If it would run away, it must be at a high potential energy. So anybody want to tell me whether it's low or high? Yes, green A is low potential. Let's see. No. Green A is actually high potential energy, but it's going to be low electric potential. So this is high U, and it is low V. And they differ, of course, because the sign of the they differ because the sign of the electron. Remember, you can sort of see it here. You can see that if you multiply the charge times the voltage, you get the potential energy from that equation in the blue box. So that's why they're opposite on this case. Now, when you go over to here, right, in this case, you're going to have low potential energy, but high voltage. Now, what that tells you specifically is that the electron is going to continue doing like we learned nature does in the first place, which is nature of its own accord goes from high potential energy to low potential energy with no real force necessary. Meaning, if you lift a turtle up to the height of a fence pole and were to release it, you don't have to add a force to it to make it accelerate down towards the ground. It's going to do it on its own. Same thing happens here. If you give something a high potential energy, it's going to move on its own. So that negative charge being next to the negative plate, which they repel it, that means it has a high potential energy and it's naturally going to move over to B if it can. It's going to do that all on its own. That's what all particles do. They go from high potential energy to low potential energy. The kicker here, though, is that the electric potential is actually going to go from low to high. But again, that's what I've been telling you is we're using conventional current, and conventional current pretends like the charge carriers are positive and they flow from the red positive to the black negative. And that's not the case. In reality, it's actually the negative charges that are moving. But unless you do the Hall effect experiment, you can't really tell. So it's okay to go with the conventional current. But the negative charges, in fact, go from negative voltages or from low voltages to high voltages. So if the electron is free to move, will its electric potential energy increase or decrease? Can anybody answer that? If the negative particle at A is free to move, will it travel from, or will its electric potential energy increase or decrease? Now I've sort of answered that already for you guys, but I did it so quickly that I don't think it's a matter of just paying attention in memory. It's more about understanding if you can get it this quickly. So can anybody see one person's already written in an answer? Can anybody tell me whether if this little green charge is sitting at A, is it going to move to increase its potential energy or to decrease its potential energy? And yes, Elron, you're right. It should decrease its potential energy because it behaves like everything does. Everything moves of its own accord in a way to decrease its potential energy. You know, people fall from heights, animals fall from heights, so on and so forth. Okay. So that's a big thing to consider. Now let's think about another problem. And I'm going to introduce a new unit. And in fact, your book takes the time. It makes this nice little table, table 23.1. And that table gives you some voltage differences from everyday life. So for instance, the voltage difference between a thundercloud and ground is usually on the order of 100 million volts. 100 million volts. What that means is that basically if you could hold a voltmeter up in the air and put the red side into, say, the ground and then put the black side up into the cloud or vice versa, sometimes there's cloud to ground, sometimes there's ground to cloud, but anyways, if you put that across there, it would read 100 million volts, and it takes about 3 million volts for air, 1 whole meter of air, to become a conductor. That's called the sort of the breakpoint voltage or something along those lines. So basically what happens is if you get a distance between a low voltage and a high voltage, and the voltage is in fact 3 million volts, if that distance is 1 meter or smaller, then the air will ionize and become a conductor well enough that lightning can fire from the high voltage to the low voltage for positive carriers, or the more realistic thing is from the negative voltage to the positive voltage with negative charge carriers. That's the breakdown voltage of air. I was saying break out for some reason, but breakdown. High voltage power lines, those ones that are on towers that you see going through country fields and mountains and stuff, those are usually on the order of 100,000 to millions of volts. And in fact, I mean, to be honest with you, there's no amount of housing on those wires that helps you. Okay. If you were in some way to touch that wire, even wearing really thick gloves, and you touch that wire, you, especially at 1,000,000 volts, you'd probably just explode. Okay. The same thing with the wires that go through your neighborhood. Those telephone poles technically do carry everything but telephone wires. Telephone wires are not run on telephone poles; they're underground, but they're power wires, and those power wires are usually, my dad told me they run 14,400, 15,500, something like that. It was some special number. He knew off the top of his head, but he retired a long time ago. But that's mostly what's going through neighborhoods. And then when they get to a pole, say outside your house, there's a transformer that brings it down to basically like 125, and then it goes into your house at that, but it's 3 phases, so you can put them together in different ways to make different voltages. So those wires too do not have enough housing to protect you. They will electrocute you if you are between them and ground and touch the ground. It's going to, do bad things. So just keep that in mind. Automobile ignition, usually on the order of 10,000 volts. Household outlets, about 100. Automobile batteries are generally 12 volts. The vast majority of car batteries, there are some motorcycles and stuff that use 6 volts, but mostly everything's on 12 volt. I will tell you though, in a car like a small car like a Corolla or something like that, you might be able to start it with, maybe 90 volts, or 90 amps or something like that, maybe even less than 90 amps. But when you get to trucks and Mack trucks and stuff like that, it's not uncommon to use upwards of a couple hundred amps, and it really only takes a milliamp to kill you. So keep that in mind. Don't be dilly-dallying with electricity. It can cost you. Flashlight batteries, AA batteries, AAA batteries, C batteries, D batteries, all those are nominally 1.5 volts. Technically, when you open them up, if you test them, they'll get anywhere from like 1.72 to 1.68. And as they slowly get older and older, the terminal voltage for them when they're not connected to anything will drop closer and closer to 1.5 and maybe even get below 1.5, and then they'll stop working. Nerve membrane is on the order of 1/10 of a volt. A potential electric change on the skin, for instance, on EKGs and EEGs, electroencephalograms is the EEG. Those are on the order of 1/10 of a millivolt. Okay, and that's actually how EKGs work. In fact, I did share that on our Canvas page. There's a book, in case any of you guys are interested in medicine, listed a book on EKGs that's really good by Dale Dubin. And I also mentioned a couple other things, some websites where you can see how this stuff works. So anyways, check those out if you're interested in the biological or medical side of the science. So now that we've gone through that stuff, I wanted to introduce you to a new unit for energy and solve a problem. So suppose an electron is accelerated from rest, or a potential difference VB minus VA is equal to 5,000 volts. So I'm going to use a green line here to cut this off, and I'm going to say an electron is accelerated through a potential difference Now, I just said that a potential difference, is that a potential energy, or is that a voltage difference that I'm talking about there, just at this part of the sentence? It's a key thing that you got to understand. Anyone? Okay, so if I don't explicitly say the word energy, then it's got to be voltage. Okay, I have to use the word energy to say potential energy. So through a potential difference, which I'm going to say is delta V, which is VB minus VA, which is also called VBA. Notice that, and that's equal to positive 5,000 volts. A, what is the change in electric potential energy of the electron? Notice I read that. I said, what is the change in the potential energy of the electron? That's the part you should be able to do. You should be able to read that and say, oh, they mean delta U. I just wrote delta U, but I want you guys to note that you are supposed to be able to read that and figure out which one they want. And then part B, they say, what is the kinetic energy? What is the kinetic energy? Whoa, Nelly. Dang it. And C, the speed of the electron. Okay, so that's what they're wanting. So what we have is basically an electron is going from a potential difference of well, a voltage of, let's say, 0 to a voltage of 5,000. That's one way of looking at it. So we can look at this and we can say this might be something along the lines of a positive plate right here that's at a VB is equal to 5,000 volts. And then over here is a negative plate, and its voltage is VA is equal to 0.0000 volts. Okay. And basically the electron is going to leave this guy and go to that guy, and they want to know what is the change in potential energy. So let's start with part A. What we know is delta U over Q is equal to delta V. That's part of that equation that I wrote up there. So I can tell already that delta U, the change in potential energy, is equal to Q times delta V. Now, technically what that means is we're going to get something along the lines of delta U is equal to negative 1.602 times 10 to the negative 19th coulombs times the change in voltage, which is 5,000 volts. I'm going to assume that it has like 4 sig figs just so we can use all the 1.602. When I multiply this 5,000 times 1.602 e to the negative 19, I get 8.010. Notice I do get a negative 8.010 times 10 to the negative 16th joules. Okay. So that is the change in potential energy. That means it actually decreased in potential energy. So is this something that it would have done on its own if you just let it go of it, or would you have to give it a push and make it go? delta U is less than 0, that means the final potential energy is lower than the initial potential energy. So that's just something it would do on its own. That's a key point there. Okay. Now let's talk about part B. Part B, supposedly, I would like to know what the kinetic energy is. So if you can imagine, conservation of energy says that mechanical energy, the sum of all of them add up to stay a constant. So whatever potential energy we had initially, which was 5,000 volts, well, that was the electric potential. Whatever energy we had initially, in this case, was 8 times 10 to the negative 16 or something like that. As that changes, the kinetic energy will change by the same amount. So if we actually set the magnitude of the change in potential energy to the magnitude of the change in kinetic energy, then we'll get the final kinetic energy. So in other words, there's a couple different ways you can write it. Remember when I taught you guys about conservation of energy, if you have me, I said U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus work out plus E loss. That was the way I did it, and that works fine. In this case, what I'd say is I am going to assume that initially we have 8.010 times 10 to the negative 16 joules of potential energy and a 0 kinetic energy, no work in. At the end, we're going to have 0 potential energy because it's all going to be converted to kinetic energy at that point. And we're not going to have any work out or E loss. So I'm going to set all this equal to 1/2 the mass of the electron, which I happen to know is 9.109 times 10 to the negative 31st kilograms times V squared. Okay. So from this right here, since they're just asking for the kinetic energy, I can already say that the kinetic energy at the end is equal to 8.010 times 10 to the negative 16 joules. And that is, in fact, the answer to part B. And of course, this was the answer to part A. And now for part C, if we assume it's a non-relativistic speed, which actually it's pushing the envelope a little bit, so it's kind of questionable for us using this, but I'm going to go with it anyways because we haven't learned relativity yet. Well, actually, you guys have, so we could do it. Anyway, so C, they want to know the speed. Well, according to the equation above, we have, whoa, I know what I'm going to do. I'm going to use my cool little lasso. And I'm going to click like that. I'm going to say copy. I'm going to click like that. I'm going to say paste. Check me out. Who's your daddy? All right, so I have all that. Now all I have to do is, well, for sure, I got to erase that stupid thing that popped up there. Evidently, I copied something I didn't mean to. Anyways, so now that I have this, I can just solve for V. And V is going to be equal to the square root of 2 times 8.010 times 10 to the negative 16 joules, which is a Newton meter, of course, divided by 9.109 times 10 to the negative 31st kilograms. And of course, a Newton meter is a kilogram meter squared per second squared. When I divide that by a kilogram, that becomes a meter squared per second squared. And square root of a meter squared per second squared is a meter per second, which is exactly what I want. So I'm going to multiply the 8.01 times 2, and then I'm going to divide it by 9.109 e to the negative 31. That gives me the square root of 1.759. roughly times 10 to the 15th meters squared per second squared. Now I'm going to take the square root of that. And that gives me 4.194 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. So it's more than 10% of the speed of light. So I'd say that's really pushing the envelope. In reality, what we should use is kinetic energy is equal to gamma minus 1 times mc squared, and then calculate it that way. But either way, we've done enough for this one. Anybody have any questions on that? Okay, well, it's almost time for class to be over. This is July 4th, the day of, so it's the July 4th Eve, if you will. So I'm going to let you guys go a little early. We've worked up through example 23-2 now. I will start from there next time, which you guys are Monday, Wednesday class, so you won't see me till Wednesday, but you will see me Wednesday. So we'll start from there and we'll finish up chapter 23 at this time. You'll notice I do have chapters 22 and 23 available on the I get you, Elron. 23 and 22 and 23 are both available on the MyLab and Mastering, as well as in Canvas. So you guys have a good one. Enjoy tomorrow with your day off, and think about Thomas Jefferson and other founding fathers and some of the positive things about our country. And have a good one. I will wait for the last person to leave, and then I'll sign off.
Professor Younger.
Yes.
I just had a quick question. So I did the midterm exam already. The last question I got was kind of like